Hello everyone and welcome to today's webinar. Today's webinar is titled An Introduction to Exoskeleton Design Using Musculoskeletal Modeling. My name is Christopher Iverson and I work here at Anybody Technology as a technical sales executive. Today I will be the host of this webinar. In today's webcast we have an internal speaker, Divyaksh Chander, who is one of my colleagues here at Anybody Technology and one of our biomechanical specialists. In today's webcast, he will share some insights in using musculoskeletal modeling within the field of exoskeletons. His presentation will start in a few minutes or so, but just before we start, I will give you a general introduction and overview of the Anybody modeling system, for those of you who are unfamiliar to the software or musculoskeletal modeling and simulations in general. First of all, I would like to point your attention to the control panel, which appears on the right side of your screen. You are very welcome to submit questions and comments via the questions panel during the presentation. We will try to address the questions in the very end of this webinar, and in case we do not get to answer all of your questions, we'll try to do so by email within a reasonable time. So let us begin with having a look at what the Anybody modeling system actually is. The Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint moments, joint reaction forces, and muscle forces. And down here in the bottom of the screen, you can see a screenshot from the actual software, so this can give you an idea of how the system actually looks. At the moment, Anybody is used in a wide variety of areas and applications, and a few examples of this is movement analysis, product optimization design, the field of sports optimization, ergonomics, orthopedics and rehabilitation, and assistive devices as, for example, an exoskeleton. And to give you an idea of the typical workflow in Anybody, it could be something like this. So you provide the recorded motion data as input, and then you can use the body models which you have built yourself or others have built. And then you can provide some kind of environment, which could be a special type of equipment or, for example, an exoskeleton. You can then use Anybody to combine these things, solve the muscle recruitment, and run the inverse dynamic simulations. This basically means that we go from motion to calculate the internal body loads and the interaction with the environment in some cases. And it gives you a simulation that looks something like this. We can then go ahead and output the results and use it for some kind of post-processing, which, for example, could be with a finite element tool. But many users also choose to complete this loop by doing some kind of design optimization, and then you can go ahead and run this cycle multiple times. And this actually brings me to the end of the introduction, and I will hand over the word and presenter role to Divyaksh instead.
Thank you, Christopher, for the introduction, and hello everyone. I am Divyaksh Chander, and I'll be talking about exoskeleton design using musculoskeletal modeling, but at an introductory level. The outline for today's presentation is I'll give a small introduction to Anybody modeling system. I'll go a little bit more in detail and compared to what Christopher just talked about, and then I will talk about application of musculoskeletal models in exoskeleton design with some examples. Then I will talk about modeling of the human exoskeleton connection in regards to kinematics and kinetics. Then finally conclusion and question and answer at the end of the webcast. Feel free to type in your questions as and when you have them, and then we'll take them up at the end of the presentation. So Anybody modeling system is a specialized software for musculoskeletal analysis. This is based on inverse dynamics analysis, and as an output from the simulation, we get the internal body loads, so muscle forces, joint reaction forces, joint moments, activation patterns, and metabolic energy. The software itself comes with an open source body models in the form of Anybody managed model repository, and I will touch upon that in a bit. You can customize your models using your own motion data and scale the model to your subject, and import CAD models to represent the environment more accurately. And then with these outputs, you can export them to finite element software or process them further in your post-processing pipeline, whether it's through Office or some other way that you prefer to do. The Anybody Managed Model Repository. So this is an open model library with a detailed representation of the musculoskeletal structure. So there are models of muscles, ligaments, bones, and joints. And this detailed data set has been obtained through several cadaver studies conducted by different research groups. And these models have been validated in several studies, and numerous works have been published using these body models. The model can, of course, be personalized using simple anthropometric scaling or really detailed subject-specific morphing using patient-specific image data. A typical workflow with inverse dynamics based simulation would be to firstly look at the kinematics analysis. So for the kinematics, you would start with the musculoskeletal model, the body model, and then you would like to provide some motion data. So the body model is doing some representative activity. And then after the kinematics analysis, then you go to the next step, which is inverse dynamics analysis, where at this point you need to know what are the external forces acting on the model. So these external forces can be measured or they can also be predicted by the software, such as the ground reaction force. And after the inverse dynamics analysis, you should be able to see some estimates of the internal body loads in the form of body joint torque, joint reaction forces, muscle activation, and so on. So when we talk about motion, which is kind of the first piece of this puzzle, I mean, I already talked about the body models previously, and now then moving on with the motion, I will talk just briefly about some of the more commonly used systems. So that's the motion capture based systems. There are essentially two types of files that can be processed readily in Anybody modeling system. So the C3D files, which come from optical marker based systems, and BVH files that come from inertial motion unit sensors. So there are models available that can readily use these files, and there are other ways that motion can be inputted into the model, but we will not look at that today. When considering forces, so there are essentially three types of forces that we are looking at in the simulation. So there's inertia force, which is due to the mass and inertia property of any rigid body and the motion it has. Then there is the environment force or the boundary conditions. So these can be the measured forces, the external forces acting on the body, such as ground reaction forces, often measured in mocap systems and mocap labs. Or these could also be the interface force between the human and the environment model. So if you have some force at the hand, these can be, if needed, these can also be predicted by the software, and there can be different ways to input these forces, whether it's analytical or synthetic forces. And then lastly, the internal body forces. So this is essentially an output of the inverse dynamics simulation, what's to find out what's happening inside the body. So we are looking at the muscle forces and the joint reaction forces. So going a little bit more in detail about the kinematics formulation. In Anybody modeling system, we use the full Cartesian formulation, and this means that every rigid segment is described by 6 degrees of freedom, 3 positions, and 3 rotations. And for each of these degrees of freedom, we need constraints in the system. So these can be in the form of joints that come between different segments, or drivers that specify the motion of one or more degrees of freedom. Normally, then we can end up in two types of system. The determinate system is a system where we have all the constraints for each degree of freedom. This means that we can write all the equations, and we have the same number of unknowns as the number of equations, and then this can be solved by the solver. In the case of overdeterminate system, which is something that we typically encounter when we are using motion capture data. So when we have C3D data with the multiple markers on different segments, and this means that we have a lot of equations and fewer number of unknowns, and we have to resort to overdeterminate analysis. So in this case, we divide the constraints in hard and soft constraints. Hard constraints must be respected at all times, while soft constraints can allow some violation. And the way this problem is then solved is through an optimization problem, which minimizes the error in the soft constraints while respecting the hard constraints. So moving on to the inverse dynamics formulation then. So after we have the motion data and we have the external forces acting onto the human model, we can frame all the equations of motions. And at that point, then we have the unknown muscle forces, and we have this problem of muscle redundancy, which is that we have far too many muscles in the human body to be solved analytically with the equations of motions that we will have. So this is solved in anybody through direct muscle recruitment. That is, the muscle forces are solved via an optimization problem, and an objective function is formulated. So there are different functions which represent different muscle recruitment criteria, and these muscle forces are then minimized by the problem while respecting the dynamic equilibrium equations and the constraint that the muscles can only pull and not push, so they are only giving positive forces. And with this one step, then we are solving muscle forces and joint reaction forces, and if needed, also the human environment interaction forces in one step. So with that, I will start then the main topic of the webcast today, the use of musculoskeletal models in the design of assistive devices. So there can be several design questions that you may have when you are thinking of an exoskeleton, such as what are the affected human variables? How will the load be redistributed, or how will it change the metabolic energy? And on the exoskeleton side, maybe how much power do the actuators need to have, or how to attach an exoskeleton to the human, and how to document the effects of the exoskeleton. So a combined human exoskeleton simulation can help answer questions like these. When we look at the literature, then we can see several examples of applications of musculoskeletal models in exoskeleton design, and these can be broadly classified in 3 different stages of the design process. So conceptual stage, where you're mainly interested in understanding the activity of that you want to assist. So you just want to characterize this activity, try to understand the internal loads in this case, and and then look at different ways and different concepts to assist this activity. So you can try to provide different joints and so on. Once a concept is identified, then you move on to this virtual prototyping stage where you try to build a detailed digital model around this exoskeleton concept. And eventually then you reach the last stage, which is the physical evaluation, where you can work with a physical prototype of your device and then test it in the lab or in the field and document the effects of this exoskeleton using musculoskeletal models. So going a little bit more in detail, at the conceptual stage, what you are looking at is to establish a baseline. So by that, I mean you want to look in detail at the current situation. You want to look at the task or activity in hand and look at the internal body loads. And then you equally important at this point is that you want to look at a reference situation to define the target for your exoskeleton. So how much should be the target load compared to the load that you've seen in the current situation. Once you have identified a target, then you would try to find the best way to assist your activity. That can be looking at by applying ideal assistance directly to different joints and look at different functions, different combinations of assistance and so on, and try to find which is the best way to assist this activity. Then once that is done, then you would probably want to move on to making a concept around this exoskeleton. So you're probably trying to understand whether active assistance or passive assistance is the best way to go about it. What kind of an actuation? Should it be a linear actuator or a rotational actuator? And then kind of come to some design specifications such as peak and average power requirement or stiffness constant for passive assistance. An example of this kind of a study is I will refer to one of our previous webcasts, simulation-driven conceptual design of exoskeletons. This was by Professor John Rasmussen from Aalborg University, and I would highly recommend you to watch this webcast if you haven't done so already. So the model that I will use as an example, this is already available in the newer versions of AMMR. And what Professor Rasmussen talked about in this webcast of conceptual exoskeleton is how you can go about establishing a baseline and a target load for the assistive device. So in this example of a box lifting activity, we normally look at the lumbar loads, which are well known to be a very critical point in this activity or a stress factor in this kind of an activity. And we also know these well-known NIOSH recommendations for the lumbar loads, the compression force at the lumbar level. And then maybe you also want to look at some other body loads, such as the patella femur reaction force. And in this case, Professor Rasmussen suggested that maybe when you don't have some kind of a recommendation available from some source, then maybe it could be interesting to consider activities like gait, and with the idea that that we have evolved over thousands of years, and we are very efficient at gait, and this is something that we can do several thousand steps every day without causing any kind of long-term damage to our body. So the reasoning is that the loads that we see in such an activity must be safe, and that can then be considered as a target level or some reference for the patella femur reaction force. And then you can, once you've identified the target, then you can look at different concepts, and by that you're just looking at idealized assistance, so you don't even need to make any detailed CAD models. And as an example, on this slide you can see 3 cases. So on the left you have no assistance, and then in the center you have rotational springs that are assisting the knee joint, and on the right you have linear springs that are acting between the shank and the thorax of the subject. So when we look at the compression force at the lumbar level, we see that the rotational springs at the knee, they don't cause any change at the lumbar level, but then the linear springs are able to reduce the lumbar loads significantly. And if we look at the patella-femur reaction, we can see that both these, the rotational springs and the linear springs, they are able to reduce the initial part of the patella-femur reaction by quite a lot. And so with that example, then I think I'll move on to the virtual prototyping stage. So in this case, you are interested in making a detailed digital model around the exoskeleton concept, and this allows you to make more reliable estimates of mass and inertia properties of the exoskeleton, and you can simulate a detailed mechanism of the exoskeleton, and then you can try to equip this exoskeleton onto the musculoskeletal model and look at issues like kinematic alignment or attachment points between the human and the exoskeleton, and then maybe you can make some more investigations with how the interface shape can affect the interaction force or how to optimize the assistive torque by changing something in the mechanism. And as an example for this is a simple model that I prepared where you have an exoskeleton that's acting on the elbow. So this is assisting in elbow flexion against a vertical load of 100 newtons on each hand. And we only have the exoskeleton on the right arm and not on the left arm. So you can see that the biceps activity on the left arm is much higher than on the right arm. And since we now are talking about some kind of a deep digital model, then we can also make some estimates of the upper arm interface force. And so we'll try to look at how changing the interface shape can change the outputs that we see from the simulation. So there are 3 cases that we will look at, and the first one is a shorter attachment arm that's on the left. Then in the center you have a case with a longer interface, and then on the right you have the case with a semi interface where you only have the interface on the posterior side of the upper arm. So when we look at the muscle activity, we don't really see any changes due to the change in the interface, and that is to be expected because we're still applying the same assistive torque in the model. So the muscle activity is still being affected in the same way. But this means that changing the attachment point or the interface can then show some changes in the interface force where you can see that the shorter interface, the shorter attachment arm results in much higher interface force, or the longer interface results in lower interface force, and the semi interface is somewhere in between. So this can maybe allow you to consider optimize the shape of the interface or the attachment point based on some of these values. And then finally going on to physical evaluation with the idea over here that you're interested in testing a physical exoskeleton, and that could be in the lab or in the field, and then you can collect some motion data using C3D or systems or BVH-based systems, and you can validate your models using some quantitative measure of the load on the human body, such as through EMG measurements, or you can also have other types of measures like oxygen consumption, heart rate, which can be a good indicators of the stress in the human body. And then along with the musculoskeletal model and the other measures that you may have, you can document the effects of the exoskeleton and how it's changing the internal body loads, and make some detailed investigations, and maybe try to correlate some subjective and quantitative measures. So as an example for this kind of a study, I will like to talk about the Andy project, where the Pixo shoulder exoskeleton was investigated in an experimental study. There were 12 subjects, and they did 5 trials with and without exoskeleton. Each trial comprised of 24 poses, and the motion was recorded with XSense, so with the IMU-based system providing BVH files, and then all of this data was processed in anybody modeling system. So that was approximately 3,000 trials, and this was a large data set that allowed to then make some individual and grouped analysis, look at detailed output for muscles and joint loading, compare between with exoskeleton and no exoskeleton cases. And then you can systematically look for beneficial or potential side effects also from the exoskeleton. And with that, then I will move on to the last bit of the presentation. So this is about modeling the human exoskeleton connection, and it's something that you could be interested in when you're in the virtual prototyping or physical evaluation, where you have some kind of a model of the exoskeleton. So this was the workflow that I described previously, and the question here is, how can we add an exoskeleton model into this analysis? So for the kinematics, we need a model of the exoskeleton and some kind of motion data for the exoskeleton. This motion data can be measured if you have a physical prototype, or it can be assumed if you are in the virtual prototyping stage. Then for inverse dynamics analysis, you're interested in the assistive force or torque coming from the exoskeleton. And you must also think about an interface model that allows an exchange of force between the human and the exoskeleton model. And after the inverse dynamics analysis, you should normally be able to see how the exoskeleton is affecting your internal body loads, so changes in the muscle activation, joint reaction forces, and so on, and maybe also some estimate of the human exoskeleton interface force. So to kind of break this down, there are essentially 2 steps that I will talk about. So firstly, kinematics and the different ways and that can be dealt with, and then I will look at the kinetics. So in kinematics, the first case would be when you will constrain the exoskeleton to the human, and this would definitely be the case when you are only working with a virtual model of your exoskeleton, and the idea would be to virtually equip the exoskeleton to maybe the motion or the activity that you recorded during the conceptual stage when you were investigating the task or in establishing a baseline. So you can take in your virtual model of the exoskeleton, and the way to do it is then to work in a determinate system. So you can each exoskeleton segment will introduce 6 degrees of freedom into the model, and then if you're working in a determinate system, then you have to add additional constraints that should be equal to the additional degrees of freedom in the model. And I just want to clarify one thing, that when I'm talking about determinate system, it's specifically for the exoskeleton model. And even though, because you might have motion data coming in from some marker-based system or BVH-based system, and you may need to work with an overdeterminate system overall for the solver to work. But just for the exoskeleton model, then you have to be precise with the degrees of freedom coming in from the exoskeleton and the additional constraints that you are adding into the system. And these constraints can be joints between different exoskeleton segments, or joints or some sort of constraints between the human and the exoskeleton. So as an example, if we look at this knee, ankle, foot orthosis from the MOVE8 project, this is a 3-segment exoskeleton model. That means there are 18 degrees of freedom, and we have 5 constraints coming in from the revolute joint at the knee joint of the exoskeleton, and then 5 constraints from the revolute joint at the ankle of the exoskeleton. And lastly, then we are left with these 8 constraints that must be defined between the human and the exoskeleton. And there can be several ways to define these 8 constraints. So you need to kind of look at your exoskeleton and work this out, the best way to do these 8 constraints or the constraints that you have. Then the next step would be mocap driven. So in this case, I'll talk about C3D based systems. So when it's mocap driven, that means I already have a physical prototype of the exoskeleton, or it could be a commercial exoskeleton that I want to investigate. And so you can take this exoskeleton into the lab, have a subject that is wearing this exoskeleton, and then you can locate markers on the exoskeleton as well as the human, and you kind of work in the overdeterminate system, in this case, just like as you would work with the human model. And then we'll have 2 kinds of constraints coming into the system. So we'll have the hard constraints, which are coming in from the exoskeleton joints, that is the joints between different segments of the exoskeleton, and the soft constraints, which are coming from the markers on the exoskeleton. And this is this way of formulating the problem can then allow you to observe the kinematics of the human and exoskeleton independently. This is how I was. So this model that you can see in the slide is the model that we worked on during my PhD, and so we had marker data on the exoskeleton and the human, and with the independent recording that we had of the human and the exoskeleton, we could see the relative motion between the human and exoskeleton, and that can be quite relevant for some investigations. But just taking on this image as an illustration and moving on to the next system, where you may have an exoskeleton where that prevents you to apply markers on the human. So you, for example, like I've kind of disabled, removed the markers on the knee in this photo, even though this is not how we set it up, but just for illustration. The point is that you will have an incomplete set of markers on the human because the exoskeleton prevents you from applying markers onto the human, but then you do have sufficient markers on the exoskeleton, and in this system you will not be able to capture the human and exoskeleton motion independently, and then you would need to kind of figure out some constraints. So there will be the hard constraints coming in from the exoskeleton joints, so different segments of the exoskeleton, and you can add hard or soft constraints between the human and the exoskeleton to make sure that the motion of the human can be solved. And then you will have soft constraints which are coming in from the markers on the exoskeleton. So in this way, you have this kind of a hybrid system where you have markers on the exoskeleton, but you also have constraints between the human and the exoskeleton. This then brings me on to the next topic, which is talking about kinetics. So now we are looking at inverse dynamics analysis, and then how do we try to ensure that there is an exchange between the human and the exoskeleton system in terms of forces and assistance and so on. So one way could be to add reaction forces, and reaction forces are typically associated with kinematic constraints. So for example, the reaction at the joints of the exoskeleton, so you can have a revolute joint with 5 constraints and you would just add 5 reaction forces at that joint. And why I can talk about this separately is because in any body modeling system you can set these reaction forces and kinematic constraints, and they can be uncoupled or decoupled from each other. So you can have just purely kinematic constraints that work at the kinematics level, and then you can have reaction forces between different segments which are just working at the kinetic levels in the inverse dynamics analysis. So these reaction forces, then they are entered into the dynamic equilibrium equations, and then we are faced with this requirement that the additional reactions in the model must be equal to the additional constraints that are needed for the exoskeleton. And this means that there are several ways to add these reaction forces, but this is also there is also a limitation in the investigation of interface force, because it's quite likely that you will exceed, if you want to add reaction forces at each interface, it's very likely that you will exceed the constraints needed for the exoskeleton, and then we'll end up in a situation where you have more reaction forces, so more unknowns than the equations of motions that can be formulated, and that just means there will be infinitely many solutions. One way to tackle or to overcome this limitation in the investigation of interface force is to use recruited actuators. So these are optimization based, so then they are minimized recruited force. So just to go back to the inverse dynamics formulation, they are these recruited actuators or contact elements, they are inserted in this objective function that is minimizing a function of the recruited force along with the muscle force and so on. And then there can be different cost functions that you can specify. So just as in the case of muscles, then these recruited actuators, they are not limited by the number of degrees of freedom of the exoskeleton, and that means you can investigate up to 6 degrees of freedom interface force at each interface. And an example of that is this sit to stand exoskeleton model, which was presented in a previous webcast, and you can look at this model on the link mentioned here. And alternatively, you could also set up these recruited actuators to simulate rigid body contact force, so considering normal and friction force. And this is how we set up the model that I worked on during my PhD. So this model for a stair assist exoskeleton. And then I would like to talk about some practical issues that we can see in the case of interface modeling. So with the way the inverse dynamics formulation is set up, we have this direct muscle recruitment where all of these muscle forces, joint reaction forces, and the interface forces, they're all calculated in the same step. And you can see some possible interaction between the interface force and the muscle force. And that means you should always look at your results critically and try to do some sensitivity studies to make sure that your results are reasonable and sensible. One of the possible causes for this interaction between the interface force and the muscle force could be joint misalignment. At least this is what I saw during the model that I was working on during my PhD. And as you may know, joint alignment can have several undesirable consequences. So you have misaligned movement between the human and the exoskeleton. That means the assistance from the exoskeleton is that the user receives is reduced, and a part of the assistance is just wasted. And this also results in some kind of parasitic interface force. And on the modeling side, it's also possible that you can see some unexpected outcomes, and this really depends on how your model is set up. So in the model that I was working on during my PhD, we saw that it unloaded some of the muscles completely, and that was obviously not a reasonable output. So we needed some ways to deal with this joint misalignment in the model, and there could be two ways. So you could just add some kinematic constraints that ensure that the exoskeleton joints are aligned with the human joints, and the other way, that the way that we used in this model, was to add some dummy segments which ensured kinetic alignment. So just to go briefly over it, is that we added these three dummy segments in this model. So normally you would have the model of the human leg and the model of the exoskeleton, and they're connected with the different points at the three interface. And so this is kind of the kinetic chain. And we added dummy segments in this chain to make a dummy leg. So this dummy leg was kinematically perfectly constrained to the human leg. So this was perfectly aligned with the human leg. And then kinetically, what we did was we had the kinetic interface between the human and the exoskeleton, and then the exoskeleton and the dummy segment. So essentially, we replaced the joint at the exoskeleton by the joint at the dummy segment. So we provided a new kinetic path for the force, and this ensured kinetic alignment during the inverse dynamics analysis. And you can read more about this approach in a couple of papers that were recently published. And but sometimes reading is not always helpful in terms of modeling in anybody modeling system. So we were glad to announce that this model that I was talking about, or in the last few slides, is the model that I worked on during my PhD. This is now available on GitHub, and you can go to this link on the slide to look at this model and open this model and run this model and look at all the different things that I talked about, whether it's the different interface models and or the dummy segments. So feel free to go on this website and get a hold of this model. And of course, I must acknowledge at this point the partners who worked on this project. So This was a joint cooperation. This model was the result of a joint cooperation between the Politecnico di Torino, which is where I was pursuing my PhD, and I was working on these issues of interface modeling. Then the Faculty of Engineering at Leipzig University of Applied Sciences, who were developing this exoskeleton model to assist the elderly in Stair negotiations. They provided with all the exoskeleton model and the motion data, and also helped set up the mocap part of the model. And the biomechanics research group here at Aalborg University, who provided very valuable inputs on how to deal with the joint misalignments in the model. Here you can see some list of publications where you can read more about the modeling aspects, and as well as if you are interested in reading about the outcome of this exoskeleton and how the exoskeleton works, you have a link to one of the publications here. To conclude then, I would just say that we looked in this presentation about how musculoskeletal models can be applied in different stages of exoskeleton design. And then we looked at how we can model the human exoskeleton connection in different ways. And we're looking not only at the kinematics, but also at kinetics, and how we can deal with certain issues that we can face in this interface models. So with that, I thank you for your attention, and I pass the word to Christopher, and I look forward to your questions. Thank you.
Thank you very much for the interesting presentation, Divyaksh. Just before we go to the Q&A session, I would just like to say a few words about our online resources and also our upcoming events. So if you want to know more about Anybody Technology, you can go and check out our website, anybodytech.com, where you can find different events, special dates, previous webcasts, and also a full publication list of studies using the Anybody modeling system. I would also like to point your attention to our other site, Anyscript.org, which is our community website for people using Anybody. And here you will find multiple online resources as our wiki page, several blog posts, links to our repository sites, and it's also here our forum is located. So you can go there and ask questions and get help from either us or from some fellow Anybody users. I would also like to announce our upcoming webcast on October 26th. The title of this webcast is The Future of Personalized Orthopedics, Kinematic Modeling to Restore the Premorbid Knee Functionality through Robotic-Assisted TKA. And in this webcast, it will be Danielle Di Mazzari, Data Science Manager at Stryker, and Periklis Tzanitis, Ph.D. candidate of the University of Twente, who will do a joint presentation of this topic. Last but not least, if you have any questions to this webcast or to the Anybody modeling system in general, then please feel free to send us an email at sales@anybodytech.com. And you can also send me an email directly at ki@anybodytech.com or reach out to me through LinkedIn. And this brings us to the Q&A session, but I would just like to thank you for your attention so far, and we will have a look at the questions.